so is everyone still awake? Yes. Okay, let's wave our hands, everybody. Okay, stretch your legs, stand up. The reason I'm saying this is because I'm going to narrate a story while you're standing up. I'm going to make this presentation between me and my PhD student, Atika. I work at Indiana University and I research on teaching learning, but I also work in the area of building teaching learning infrastructures, which is basically how do humans and machines learn together and be able to interact and make some impact. So about impact, I'm going to say a small story. So while I was finishing my PhD, I wanted to get into academia. I had sold a company, I'd made enough money, and I was thinking industry is great, it pays a lot of money. I don't know what I want to do with my life, but industry seems like a good place to earn money. I was finishing and I had submitted my dissertation and I went to a conference. And suddenly I went to this conference and I met a middle-aged woman. Some of you might have heard this story before, some of my students, but so I met this middle-aged woman who comes to me and hugs me, and I don't know who this person is, but I just keep my hands like this. And she says, "Do you recognize me?" I said, "No, I don't remember who you are, but I'd like to know you." And she says, "Please watch my presentation, and you'll remember who I am. Go to this track, this room." So I said, "Okay, let's go." So I sat there and I saw some presentation. So a few years ago, I worked with the government of India and I built an app in 3 weeks, a mobile app, and that app got deployed to many, many different sites. But one of these sites where she was reporting data from, that site had a maternal mortality rate, which means the number of women who die for every 100,000 live births was at 40. So 40 women used to die for 100,000 live births. That's a very large number. Some of the poorest health outcomes in the world are at that scale. And then she was showing her presentation that this was in 2010. When you did this, by 2013, in 3 years, they had reduced that number from 40 to 2.8, right? Dramatic decrease, right? And the way she was attributing it is because we implemented this mobile technology, we implemented this health system resource monitoring tool. That's why we saw lesser women die. And I internally knew that's not true, right? It's because it is visibility of work, what people do that's getting visible, and then people make decisions based on this data that's available, right? So information is care is the motto with which I work. And then I realized that doing this work is truly going to save lives, and academic research or research to find discoveries and things like that, that truly saves lives. And that's basically what brought me into academia and changed my life to what I'm going to show you today. But what I do here is based on that. So please have a seat, everybody. Sorry to keep you waiting, but I wanted to get you to remember what we are going to do now. And all of the work that we are going to do now is going to be hands-on. So you will do it while I'm doing it. So it's no watching, but rather you have to do. So I want everybody to connect to the Jupyter Lab. But while you're doing that, I want some interaction. I want you to speak up why we need artificial intelligence or why machine learning or whatever. I have 3 figures here that are path breaking in the last decade that has truly transformed the world in a sense. And can anyone tell me what the first image on the top left is?
It is against the world champion. I think he's from Japan or something. I'm not sure. It's a AlphaGo. Yeah, it's a app. So that person like kind of defeated the robot was defeated by that person after third time.
Yeah, so that top left, that's Lee Sedol, who's like the greatest ever Go player. So Go is a game that's supposed to have many permutations and competition and computation, and you cannot just remember the board of the number of spaces and make that prediction, which is what you do in chess, but not in Go. So there are too many permutation combinations that are available. But Lee Sedol, the best human who has ever played this game, at least for practical purposes, was beaten by this machine many number of times, and it did not get trained on a lot of computing. But what was new in the way this worked was, you can watch this nice documentary on Netflix, but the idea is that computation is so powerful today that what we thought even like 15, 20 years ago is possible today because of that. On the on this image, can anyone tell me what this is? What this breakthrough is? The bottom image here. ImageNet Challenge, right? So ImageNet Challenge was started in 2010, and this is a top 5 error, which means 5 classes that you make the least error on, and these are images, and you have to identify objects within those images. So it's an object detection challenge, and you can see something dramatic happened between 2011 and 2012, right? There's a dramatic drop in performance, and that comes from training models that could be done on GPUs or graphic processing units. So computational power got truly reduced at this point. And today you see it's like humans are not at all competitive in this arena because they do really well. And today, when AlexNet was trained, it took about 40 to 50 hours to train that model. Today on a mobile phone, you can do it in about 20 minutes, right? So computation power on a low powered device compared to a set of large GPUs is so strong. So computation has truly accelerated because of GPUs. That's the lesson we learned from this. And does anybody remember what that is, or does know what the top right image is? Transformers, right? So that's the other big change. So I listed the 3 main things. Transformers is a way in which, a mathematical way in which you make attention, which we'll talk about hopefully sometime later during the datathon, but that has truly transformed what things a computer model should focus on and how it should forget things that are not important and remember things that are important, right? So broadly, these 3 have transformed or changed machine learning. And I say AI, but AI in that I specifically focus on machine learning. So all useful programs learn something, right? You're writing the program because you want it to do something, and that doing comes probably from learning. So the first example I ask is, do you think predicting square root of a number or calculating the square root of a number up to some error, is that learning for the model? Like, is the model learning something, or is the program learning something? How many of you think that it is learning something? Please put your hands up. No? No one thinks it's learning anything. Okay, so what is it doing? Like, how is it doing it? How does the program tell you what the square root of a number is? It's not learning. What is it doing?
Oh, why me? So the program, sorry, because the program is, you are just learning to calculate the square root. That's what you're saying.
Mhm.
You are training a model for that, or you are just asking the model?
Just asking it to.
Well, there are 2 ways. You can compute it, or you can just learn it from examples. But yeah,
Okay.
you can basically go both ways.
So you could learn, right? So it's not a problem that is not learnable. Is that what you're saying?
I mean, it's not the best approach to me nowadays if you think about, I mean, you ask that ChatGPT or something. Most likely it will detect it and it will go to an agent that computes that and return the answer. I'm not sure it will really learn it from, like you learn to make predictions with a language model, right?
Yes. So that's the sort of nuance I'm asking you to get to, which is you can do it analytically, which means you can create a formula, and from that formula, give the program the formula, or let it learn it from the data and create this formula for you, right? So I think those are 2 different ways. One is analytical approach, and the other is computational approach, where you are learning from something, right? I'm not saying either of those are not learning, but when we think of machine learning today, it's primarily computing rather than analytically doing it, right? And then to be able to get to the computation, you sometimes do something analytical, and we're going to talk about that a bit. So this is basically what machine learning is. It's a transformation of writing a program as an input to getting the output as the program. So we are basically trying to create the formula, which is the program, for based on the data that it's observing, right? So square root of a number you can think of traditionally, analytically, as you give it the formula and it calculates it. And here, curve fitting for linear regression, which means you've been given data and now you're creating that formula. We all know y is equal to mx plus c is the formula for a line. If you didn't, let me tell you that is what the formula is. Y is the value on the y-axis, and x is the x-axis values that you have, and m and c are things that the program learns, right? So finally, you can, for any values of x, if you know m and c, you can get what the value of y is, right? I'll skip all the math, but I'll talk about what kind of learning you could do. So you could do memorization, which is rote memory, and it's called declarative knowledge. So here what we are learning, we are not talking about declarative knowledge, right? So you look up every possible square root that exists for every number, and then you just search through it and give it out, right? That's also a different kind of learning, but that's called memorization. But that's not what we are trying to build here. We are trying to learn the way in which the numbers were generated, right? To calculate the square root of a number. So the problem with declarative knowledge is limited by space. So you have to remember and memorize. So you have to read everything in the world to be able to answer questions, right? Which is not practical or feasible. The other idea is generalization, which is what most machine learning does, which is it learns based on what fact it's seen, and then it tries to interpret or create new forms of outputs that correlate to the pattern that it's already seen, right? Basic paradigm of some glossary terms that you should know of. Training data is the examples through which the machine is going to learn. Then you infer something about the generated process. So create a formula of sorts of the thing, sometimes called function, but could be called formula. You learn what kind of formula it is for the prediction that you're making. Then you choose what numbers or what kind of task the model should do. And then you actually test it on data that's not seen. So that's called test data. And there are three large paradigms that I'm going to talk about for machine learning today. The first one is unsupervised learning. So you do not tell what the labels are, or you don't say like these are the facts and these are the outcomes of those facts, right? We don't know that. That kind of is the first part, which is unsupervised learning. Within that, you can think of clustering facts together, similar objects you put in a box, right? So if you have a round shaped things, and we are thinking of shapes, so we put all the round balls together, the cubes together, the triangles or pyramids together, and things like that, right? So that's called clustering, where you put things, similar ideas that you think of, and these ideas are basically features. So you bring those common features together, and you don't define it in advance, but you just keep discovering what features you want to define, right? And then there is also dimensionality reductions, because if you think of, there are so many kinds of characteristics that you can identify. So we limit that space to what we think is relevant. So you need to have some kind of domain knowledge to be able to identify what this unsupervised learning mechanisms are going to be. Then there is the supervised learning aspect, which is you can classify things. So you already know what is important to you. So the example that you saw in the previous presentation was sort of that, where you know, like there is D-mimer or some other test or something else you've already captured. Those become features, and then you're saying somebody would have serious consequences due to COVID or not, right? So you're then staging how severe the COVID infection would be or outcomes would be and things like that. So that you can think of as classification. The second kind of supervised learning approach is regression, where you're trying to predict a specific value. So if the person got sick, what their and the body temperature is going to be, for example, or how many days they would stay at the ICU. Something like that, which is a continuous number, and you're trying to make that prediction. So that's called a regression task. But again, you have fixed features that you want to use, and your outcome is also sort of either a categorical variable, which is 1, 2, 3, or some positive, negative, things like that, or it could be a continuous variable, which is like regression. Is that clear? Any questions, anybody, on this? And the last part, which is often skipped by a lot of people, which is very important today, it's called reinforcement learning, which is you don't necessarily decide in advance, but you observe how somebody did a process. So that's commonly how humans learn. So you observe something, you see the outcomes of those. If there is a reward, then you do that more. If there is a negative reward, then you do it less, right? So carrot and stick, the way we train babies, all of that is sort of reinforcement learning. So you observe a process, see what the reward is, or if it's a negative reward, you don't do it. If it's a positive reward, you do it, right? So that's how we train humans, and there are different applications that I give. Yes?
How is that different than a supervised model just using a loss function to get to?
Yeah, because I don't think in the supervised learning model, we didn't necessarily give reward to the agent that's observing it. So there's no live continuous updates to it in the same sense as in a supervised model is. So, so what we're going to talk about today and what we're going to try is this, which is an end-to-end machine learning process. So what is it that you do from the beginning to the end to build a machine learning model? So what I'd like everybody to do now is to go to a link on their browsers, and the link is at Is there a shorthand URL to this? No, right? Okay, let me copy this and put it on the slide. So everybody please point to this GitHub on your browsers. We have the slide also there. So if you want to add something to your notes or anything else on like a send a pull request, if you know what that means. But please go to that link, and once you are at that link, we have 3 notebooks. I'll get to what a notebook is. I didn't want to put a QR code because if you did the QR code, it'll open on your phones. So that's not what we want. It's not working for you? So github.com, A caps, R caps, P caps in this, and then Emory Datathon _ 2024. Yeah. So I think that it's not working.
Put it in the summer school help, because that's the only one I have access to. But I was reported to the general.
Yeah, Emory Datathon _ 2024.
And we'll bring some power cables at lunch.
Okay, are we all here? Anyone who's still having issues Atika can come and help you out. Or you can respond to the Slack and I think we can look through that. Okay, so the first step is to formulate a problem, right? So let's think of what the different problems are. This is, to contextualize, this is at the ICU. If you know what, it's an intensive care unit where people would go in for a short duration and they would be put back into an inpatient after they are less severe. So that's an ICU. So what's important? Can you think of different problems that are important here? Length of stay, yes. Number of deaths, okay. Okay, effect of treatment, yeah. Somebody else said something. Use of ventilation, okay. Yes. Most common conditions, yeah.
Predicting when you're going to get out of the ICU, because ICU beds are very expensive.
Yeah, so maybe a time duration or maybe time of the day when they might be discharged, or time of when they could be. So scheduling is important. So knowing when would the beds be available, knowing that beyond the length of stay, yes. Staffing, yeah. So because if you know how many patients are coming in, you can staff and things like that, right? So all of, yes. Secondary infections, yeah. So before admission into the ICU, what was the case, and then after they are admitted, what is the case? So within the first few hours, that could be identified as secondary infection. Anything else? So all of these are great ones, and the datathon you can think of formulating a problem, but some of these, like we said, are a category of tasks that you can perform, right? So length of stay, it's a continuous variable in number of hours, right? So let's look at what that is. So length of stay, for example, in a data set is usually measured in days and not hours. You could convert that and translate that to that, but that's the code, that's the data, the way it's been coded and made available, which is in days, right? So how many days you've been within the ICU. There are other important predictors that you can think of for length of stay. So these could become features, right? So all of these features will allow you to make a prediction about length of stay. So there are things of demographics, there are things of admission details. So what type, was it an emergency, elective, location, your insurance? All of these people have shown has an impact on the length of stay. And the specific set can vary depending on what predictive model you're using. We'll go through some of that. So we start with the second part of it, which is data acquisition, right? So the data is provided to you in the folder, as we had mentioned. So this data has been captured from the ICU, and then you can look at the way the data is formatted. Where is the data available? So you can see, please, once you go to the repository here, please download these 3 notebooks. So these are called notebooks. They end with the file extension IPYNB. So the way you download it is you click on one of these. After you've clicked on these, on the right hand side, you'll see a download icon, right? Download raw file. So please press on that one here on the top right. Click on that. Do it for all the 3 notebooks because we're going to use those. And the other file that we have here is the PDF for the slides. So we got some feedback from the first session. Having slides available is a good thing. So we have that available. And we're going to go through each of these. So now that we have formulated a problem, let's try and calculate length of stay first, and then we'll do a different task But length of stay is a regression task, right? I said it's a continuous variable. So it is number of days, and that number of days is a decimal number. It could be half a day, 0.5, more than 2 days, 2.4, something like that, right? So that's the data that we have, and the format in which we have the data is called Parquet. So the first thing we need to understand is what does the data format look like? So Parquet is a big data format, so widely used as a standard. It's an open source data standard. It's available in a column-oriented format, and what I mean by that is that if you see the column 1, 2, 3, 4, 5, product, customer, country, date, sales amount, you see that you can actually group things within those columns based on their values and not read the other ones. So it is very fast memory saving because you don't read the entire thing. Whatever categories or what parts you want to select, you can do that. And you can select what columns you need. So each of the columns are in the memory on its own, which is why if you only want to select, say, 2 columns, the data will load only those 2 columns with the filter of the row that you select, right? So that makes it a very efficient format for memory, and it works really fast. And that's why Parquet is a great format for big data, right? So that's the first thing you should know. There are other formats like CSV, JSON, and you have a table comparing all of them. Why Parquet over other ones? So whenever you work with big data, I recommend you format your data in Parquet and work with Parquet. And it's a pandas native. So if you've not heard of pandas, it's a data processing library in Python. So we're going to use Python as the programming language. I'm assuming most of you know or understand Python, which I saw one group also mentioned during their intro that they all coded in Python. So good. But there are statisticians who do R, but the ideas are similar. So I hope you can adapt based on that. So the first thing is to read the file, but to be able to read the file, let's log into your your labs that was set up. So everybody's logged into the lab. Once you are in the lab on this screen, what you do is don't create a new notebook, but upload the notebook. So this icon that you see, okay, so once you're in your lab, this icon, which is upload, on the left here. So please click on that and then upload the 3 notebooks that you downloaded of GitHub. And you'll see them here on the left, right? So everybody's with me. Anyone with any questions on this yet? Yes? No. Okay. Anybody who's stuck or has questions? I know some of you are probably very familiar with all of this, but I'm trying to go from the lowest. Okay, so let's open the first notebook. And this is what a notebook looks like. So the reason we've been calling it a notebook all this while is because you have things that are documentation in a language called Markdown. Again, details you don't need to know, but it tells you something that it's not going to get executed. And then there are these cells that you need to execute, right? So these cells have the code that you need. Please press Shift and Enter key on your keyboard, or you can also press the Run here. So this runs your code if you're not familiar with the notebook environment, but you basically have to install some packages. So what we're doing here is running pandas, pyarrow, and matplotlib. All of these libraries, like I said, pandas is a pre-processing library or a data processing library. Pyarrow is to be able to work with Parquet files and be able to do some fancy filtering and those sort of things. And then matplotlib is a visualization library that allows you to visualize how the data looks like, right? So please install this. We are using pip to do the installation. I hope Aviz thinks it's okay. I didn't ask him before. Pip is good. Okay. There's also conda, and that both of them don't work together very well. Okay, once you're done with that, you import pandas. If it tells you no module named pandas, is because you just installed these packages. So you have to refresh what is known as the kernel. So please go to kernel on the top here and say restart kernel, right? Once it's been restarted, you can load the libraries that you just downloaded and installed on your user account. So everybody is good. Most people should have got that error. Sorry? So here, you should click on kernel, restart kernel. And once you've done that, it'll ask you, do you want to restart it? Yes, sir. You say yes.
One thing that I noticed is if you do, and I put it on the Slack, if you do the exclamation mark, it doesn't load it in your kernel. So just do the percentage sign. So do the percentage. Then it's gonna then it's not gonna load in your thing and won't restart. Just
Okay.
do the percentage.
Or hash. Hash, right? Like this? Oh.
Install it.
So you think this doesn't work? This should work.
No, it does, but then it doesn't load it in. But yours seems to work.
Yeah. So please uncomment. So I wanted to demo that also. So you have to uncomment the first two lines. If you saw the first two lines, those had hash in them. So there was a hash, which is basically a comment. So once you uncomment the first two lines and then install it, it should work. But a lot of times libraries will not load as soon as you've installed them. So which is why restarting the kernel is a good lesson to learn also. And then once you run this, after this, there should be no errors. I hope everybody is fine now.
Let's
Yeah.
get to the admissions. Who's gotten to the admissions? Who's not gotten to the admissions? Just lift up your hand so that people can help you. Who's not gotten to admissions? Yeah, I see neighbors helping each other. Those are the calls too. Yeah. So that table, who's not gotten to admissions? And all we're doing right now is familiarizing yourself with Jupyter. You've been able to load a data set, right? And you can see the admissions table.
So PD is basically pandas. So we've used pandas and reading the Parquet file and be able to get this table out here, right? So everybody's got this output,
Yeah.
basically what the table contains.
So who's not gotten there? Don't be shy. I mean, there's so many people to help you in the room. Okay. Okay.
Okay, I think that's great. What we want to see is what are the unique values in subject IDs, and you can see there are a lot of subject IDs, but really what we don't really want to use this information, but wanted to show you how to get unique values. So you just say subject ID, you've selected a column. So this is how you select a column. So subject ID is being selected from this data frame, and we are saying show unique. So these are unique ones. And you can also do not unique. You can also do number of unique, how many of them are unique. So you can see there are 492,100 patients who have unique IDs in the admissions database. So these many admitted patients in the ICU. Is everyone with me? Yes? Okay. So then also we can see there is a race column, as you saw here. So these are all the columns when you look at the data frame. What you see at the top here, these are all the column names. Again, these are not coded, but they are just variables, and you could actually give a long name to it, but we'll use these ones. So here we are using the race column, and we're doing value counts. So the value count function tells you, so Caucasian or white, 463,000, African American or black, 475,000, 435,000. So now you might wonder, why didn't we say we had 492,000 patients? And the sum of all of these is not turning out to be that, right? Can anyone tell me why? Admissions, right? So please remember this. So when we looked at unique patients, we saw like these are the unique patients, 492,000. And now what we're looking at, we are not doing the unique anymore. We are saying just give me value counts of race, right? So we have many patients who have been readmitted in the data set, actually nearly double the patients. So every patient has probably gotten multiple ones. Some of them have got just one, but others have got 3, 4, 7, maybe. So all of that is going to tell you like what you're trying to look at and try to understand what the data is reflecting for you, right? So being able to understand this is important. Yes. Yeah, so these are in the data. There are some of these that have been coded already, and they may or may not be real values, so we should be able to ignore them out of this. And there are too many races. Maybe you don't need all of them. But what I wanted to show is the difference between unique patients and then also multiple admissions. You should not be confused between those things, right? So we load then pyplot. Matplotlib has a function. Now each of these packages behave differently, and there's a lot of depth to it that I'm going to skip here. But for example, if you wanted to look at the same value with bar charts to look at, I know we have a later session where we go into visualization in much more depth. But here I'm just going to show you the same values that we saw now as bar charts. So you can do something like this fairly easily. And these are really small values, so we're going to skip those later. There are too many classes, so what do? We combine them into fewer classes of values. So 1 becomes others, 2 becomes others, 3 becomes others. We don't really need to know what these are because we're going to categorize and bundle them together. They're fairly small, as you saw here. The numbers were really small, right? So then what we did was put all of these, if your problem that you're looking at hand it involves these things, then you shouldn't be putting them in others. But here, I'm just showing you how you put them, relabel the data, right? So that's basically what you're doing. And here we are doing a different kind of plot, yes.
Everybody understand that remapping? Questions on remapping? That's a pretty big step that we do for cleaning up data. So good. Check. Everybody understand the function of remapping, why we do it? Okay. Yeah, sure. So EHR data is intrinsically noisy, and it goes through several variations over time, right? So at Emory, up until 2022, we were using an EHR called Cerner. Now we're on Epic. Data then, goes out of a EHR system into a clinical data warehouse and undergoes a transformation. That's what we used to do with Cerner data. Now we have Epic data is accessed directly by Clarity. The conventions for coding race, ethnicity, or really anything, whether it be a lab, will change over time. We have big transition from ICD-9 to ICD-10. So if you're dealing with a large set of retrospective data, you will invariably get multiple, you'll basically get results like this. African American may be coded in 3 different ways. You will get things like 1, 2, and 3, or CD 1594, right? And then it's up to you to decide how those things can be combined, whether they should be discarded, whether they're reliable. That's where sort of like that domain expertise comes in. But if you want to do some sort of evaluation on, a model performance by race, and you have a class that only has, 10 patients or 20 patients or less than 1% of the data, it can be really tricky. So sometimes our imperfect solution to that problem is to lump those things all into one other category. And that has its own set of problems, but at least you sort of clean the data. So this is all really in the data, sort of data cleaning step. It's important to know that these transformations are done, right? So somebody who receives this data after it's already been harmonized won't have that insight of what's inside of the category that we remap to other, right? So as when you're working on projects like this, try to go back as far as you can and go to the source so that you understand what transformations were done. And I've as stated this already, but I'll restate it. Pretty much every data type we deal with will have to go through some sort of data cleansing or reduction of variability.
Yeah, and everyone who's worked on practical machine learning will tell you that 85% of the time is spent on data cleaning, pre-processing, and all of that. And about 5% is model building. And then the remaining is validating in the real world or something like that, right? So that's the amount of effort it takes, where most people think this is grunt work, and this is not useful, but this is what takes the most time. And the more time you spend on this, your models will turn out better later on. And then we visualize this after we've done the mapping. And if you missed how we did this, there's a dot replace mapping. So this mapping is basically replacing what we had, and we're able to produce numbers like these, categorization. Now this we are just showing you for race, but there are many other variables and categories that you have to do this with. And without domain knowledge, it's practically impossible to do. Or if you do it without the domain knowledge, you're doing it wrong, very likely.
So what I want you to think is like, wow, you're seeing all this code is moving so fast. Number one is if you copy just the code snippet and say, put it in GPT and say, explain to me step by step, it would do an amazing job to do that, right? So that's why we cannot teach you coding in 1 hour. We want to teach you the mental model that is required to approach a problem, right? So we started off with the CPATH data. You're like, okay, how do I deal with this messiness? You really don't know, right? All of us would deal with it differently. So this is trying to introduce the concepts of machine learning to you, that especially just the traditional stuff. So we wouldn't be explaining what these things are as we move on. But the second thing is you're seeing even different visualizations, right? So we want you to get comfortable with the Jupyter notebook so you can start to play with things as we go along. But here is like, how do I approach a problem, right? You should look at through like pandas describe your data frame, and then you start looking at just unpacking every row to say, what does it mean, right? As Harry said, then at that point you make a mental model that helps you to move on to your project. But this is a specific case that we took that we want to show you end to end what it looks like.
Then there's the other one that we'll load, ICU stays, because length of stay is there. All the patient information was in the admissions, length of stay. And this is a fairly well-known format now. Mimic first released it and created this format. And basically, with help from the Mimic team last year, we were able to transform it into this format. It's a proprietary data model format. You could do it in OMOP or whatever, but there are a lot of tools available to be able to do with this model or this data structure, and that's what we're using for this. So we load the ICU stays table now into a new data frame. Instead of DF, now it's called DF underscore ICU stays. So we can look at the same thing here. We look at two variables: first care unit, which is first where they were from the inpatient ward or directly from emergency where they were brought in the ICU, and then what the length of stay was, right? So as you see, this is a decimal number because some of them are less than 1 day, but there are many ones that are fairly long as well. And if you think of where they are, there's probably a correlation, right? And we'll try to look at that, is if there is a correlation with what site you were at, what inpatient care unit what ICU unit you were at, and the length of stay. Maybe there is some, maybe there's not. We'll try to find that out, right? But what I'm trying to tell you is how to think of the problem rather than the code of what we've done, but think through all of these issues when you're coming across this. And then we looked at what the average length of stay was at each of these facilities. And when you see average, the first thing you should think of is what am I losing, right? When I'm doing, this is the mean that I'm calculating, although we call it average here, it's actually mean is what we're doing. And then we are looking at where these means lie across different sites. And like I said, maybe there is a correlation, maybe there's not, but that's good to do when you look at data like this. And then we can also plot this as a bar chart. So I hope everybody is executing all of this, because what will allow us to do in the end is to be able to extract this data into a file. So they should be fairly fast to do the output of it. Anyone who's having any issues when we are executing this? Okay, so the average length of unit, and you can see we've plotted it, merging diagnosis codes and the title, right? So now we know all the, maybe you don't know, but all the code, all the, for billing purposes is converted into a code, and that code is basically used for the disease that the person had. And many a times this is not the actual problem, but basically for billing purposes, that's identified as the code, right? So that is with having that knowledge that let's still try to put some value with that code so that you can actually read what the disease is, because nobody memorizes all these codes, right? So that's what we're trying to do here.
So I want to make one clarification point. ICD codes can be really, really tricky. A lot of EHRs and data warehouses do track the reason for admission ICD code, which can be more reliable. So an admitting provider will select the disease or diagnosis that was responsible for the admission. If you can get your hands on that, that's a little bit cleaner, although it's imperfect. If somebody has diabetes, hypertension, heart failure, and comes in with volume overload and an infection, right, that their reason for admission is truly multifactorial. So whenever you're dealing with ICD codes, though, when these come out from most data systems, it will give you all of the ICD codes associated with that admission, which means that if somebody's admitted to the ICU and they have COVID-19 and 5 comorbidities, all of those ICU codes will be reflected. So take ICD codes with a large grain of salt, because it's also all of the diagnoses that the patient carries that may or may not be related to their admission. So these can be really, really tricky. International Classification of Diagnoses, of Diseases. International Classification of Diseases. There's a ICD-9 version. What was it, 2015 it switched to, and then ICD version 10 now. So these can be found online. I don't know, 50, 60,000 different diagnoses that are coded, and then you can find the actual, what the actual entity is.
So yeah, most of us will end up, you need an anchor, right? So if you're saying, I need to know what the patient, and we discussed this a little bit when we were preparing the talk, about how far to go down this rabbit hole of ICD code versus CPT code. It's very, very important if you're going to work with any data. So sometimes you'll never get the date stamp of the code itself, and that would be a way to say, for example, because you may have come in with maybe what was thought to be a heart attack, but later on became a new diagnosis, right? So your diagnosis can change in a hospital admission, right? So if you don't have the times code of the ICD code placement, then you completely lose it, right? And then there's an issue of harmonization between ICD 9 and 10, right? And then there's also sort of there's some people who have the primary diagnosis and the secondary. So it's so variable in how it's captured. And most of us will rely on either, so Harry leads a lot of our data curation efforts. So this is a pain he has to encounter every time. But most of us will just rely on seeing if there's a paper that's been published that has described a lot of the methodology and starting there, and then going back to say who's missing in terms of just the same grouping and data transformation. But this is a big, big issue for working with any tabular clinical data.
In general, if you can avoid ICD codes, it's better to avoid them. They come with a lot of problems. So if you can get clinical information from some other source like CPT codes, which we may talk about, like procedures, those are indexed to a time that's something that was done to the patient. So for example, the ICD code may say something like heart failure or heart disease or coronary artery disease. You don't know when that diagnosis was initiated for the patient. You don't know if they've had a heart attack. But if you see a procedure, a CPT code for stent placement, you know that that patient experienced an event that required placement of a stent in the coronary vessels. That is a much more reliable data point than and so in breast cancer, we deal with this a lot. Somebody have breast cancer in their ICD diagnosis, it could have been from last month and it could have been from 20 years ago. And most of the times you don't know. So if you can avoid using ICD codes in many aspects of training your model, they're actually better to be avoided.
Thank you. Yeah, I think that nuance is very, very important. And we'll go over some examples to see um, what people had in their ICD codes through that. And this is only one example, like a really short one. Like I said, 85–90% of the time on building a model is spent on this work. A lot of grunt work that requires domain knowledge. We'll read another file here, which is the ICD diagnosis. This is the name for the diagnosis code that's available. So that's what we are doing. So another kind of mapping that we are doing between term and the code. And this mapping allows you to get to things like displaced fracture of the greater, something which has this code. So if you find that in the ICU stays, that this person who had the ICU admission had that code, right? And may not be the reason for admission, right? A few more tables we add because we are trying to build this um, this artifact that describes what the patient had, or is different kinds of things that the patient could have had that could be related to predicting length of stay, right? So a lot of times the way you should think of model building or being able to do machine learning is to have some intuition, some knowledge of what targets you're going to use to hit, but it's still hitting in the dark, right? So that's what nuance you have to understand, that it comes a lot from intuition and experience that you've had understanding the domain. So we do that, and here you see we're converting some data types because they are in formats that may not be useful for model building. So this is another thing you need to look into. So we get that, and after we've merged all of this, this might take a little bit of time for you to get to, but it produces something like this. Um,
If you successfully run this, you'll have in your home folder something called dear admissions.csv. And that's something that's just merged, um, that's something that's just merged. That's something that's just merged a little bit of the data set so that you have something to work with. So when I approach this with students, what I say is, what's your parent cohort? If you are in, for example, in an ICU length of stay prediction, do you care about the patient or you care about the admission itself, right? Because that's going to force you to look for data in different cohorts, right? Or do you want to look at patients with sepsis, right? Figure out what your left cohort is, and then you start merging things to it. Some things will blow up, like for example, a patient may not have just one ICD code and will have multiple ICD codes, so you should look at that. Or versus, and it's going to say, maybe if admissions is my table, because I want to model and think who's going to have more than one admission, right? So that's your problem formulation and writing it down, including what you think you should approach it. And then, honestly, if you're not doing data discovery, trying to come up with a hypothesis even before you look at the data is probably one of the most important ways to approach a machine learning problem. Because if you say, I expect that the patients are not worth more than 130 years, right? Then what you're doing in your data set is going just to prove that, that is different. And then you end up with your final cohort of cleanliness. Now, the way we've transformed our data, like Saptarshi said, we had Alistair last year, who's unable to join us this year, who transformed the Emory ICU data to the Mimic ICU data. So if you've published a paper using the Mimic ICU data, or you have an idea or you love a paper that was done, you could pretty much look at their code and rerun it on the Emory data, because the structure of the data is normalized to that format, which makes it easy for you to do those type of tasks. So here is just showing you how are you making some of these things. You can put some of the sort of like the big codes that you don't understand and say, explain step by step for me. And, then we'll move on to sort of like, this is what you would have to clean and some of the big pitfalls that people make as you approach tabular data.
I do see a couple blank stares in the room, so if you have questions, please ask.
So you should have that BF admissions.csv. If you don't have that, you've not run through the editing.
How do we know each column's meaning? You know, there are so many columns that I really don't understand them.
So that can be tricky. I mean, for this purpose, we can obviously go through and explain them. Hopefully, columns are named in a logical way. So reading the column name is sometimes the best. But sometimes you have to go back to the person who extracted the data and ask what these various columns mean. We can certainly go through and maybe delineate what is in each column, but that can be tricky, right? We get these pulls from the data warehouse. They tend to have the same column name, so after you've dealt with it a few times, you understand what's in each column, but that's a challenge. Yes.
Are we allowed to download the file? Yeah, just keep it where.
Keep it where, yes. So,
Good morning, everyone. I'm not wearing a t-shirt because I just got off of an airplane, but what Professor Judy was saying was incredibly important about the idea of hypothesis generating first. For those of you who are not clinicians in the room, I want to tell you a horror story. The horror story is a whole bunch of very, very smart computer scientists and data scientists who independently discovered that it seemed that only men got prostate cancer. What was their first mistake? Someone tell me their first mistake. They didn't talk to a clinician. That's right. So when she said come up with a hypothesis, please make sure it's an intelligent one. Go and I'm serious. I know it sounds stupid. I know it sounds like a joke, but this really happened. Please go and talk to a clinician and say, hey, this is something that I want to study. Is this a result that is worth your time? If I found an answer to this, would it move medical science forward? Then go forward with it. There are going to be some times where I'll talk to one of my oncologists that I work with, and they'll say, Professor Odom, that's actually a really stupid question. And that's fine. I am okay telling me that I'm asking a stupid question. I ask them, okay, well, why is it a stupid question? Then they explain some rudimentary understanding of biology that I forgot about. There are other times where they say, well, that's an interesting question, but I don't think it would help anyone. And then my gold one is when they say, ooh, that's interesting. As soon as I hear an oncologist or a clinician say, ooh, that's interesting, I know I've got some place to work.
yes.
So you determine the average length of the stay based on the comorbidities a patient has, or you want to grab more money in the ICU? I was just kidding. It depends, right? So how do we know that the length of the stay is solely dependent on the comorbidities a patient have, or maybe he's rich enough to pay the bill?
So the question was, how do we know that the length of stay is not confounded by some other factor and really related to how sick patients are? So it turns out that there's a concept called DRG, which is a diagnosis-related group. You get paid for an admission based on the diseases or conditions that a patient has, and not necessarily based on how long they're in the hospital. So we get paid in the US healthcare system, which has a ton of problems, but the US healthcare system is paid on a fee for service. So you provide a service, you get paid. If somebody's in the ICU with sepsis for 7 days versus 3 days, you actually don't get more money for that. So hospitals on average will lose more money when patients are in there longer, which is why there's a big push to actually reduce length of stay. Now, if that patient is there for extra days and gets extra procedures and scans, that's additional revenue for the patient. But on average, a hospital system will save more money by getting patients out quicker. So you can be, at least somewhat confident that length of stay is not artificially inflated for the hospital to make more money. Now, it may be artificially low at the expense of patient care because the hospital wants to make money. So you actually have the opposite problem. It's a great question. Yeah. 。
Uh, 。 。 。 。 。 。 . 。 . 。 . 。 . 。 . 。 . 。 . 。 。 . 。 . 。 . 。 . 。 。 . 。 。 . 。 。 . 。
Yeah.
。 . 。 . 。 .
So
So for this data, for example, admitting, and does it mean that they are in the ICU or they went to the doctor, or for example, these things are also a little blank to me.
So these are specifically ICU admissions. So we could get data on outpatient visits. You could get data on ER visits. This data set is specifically when a patient was admitted to the ICU for this data set.
But that's a great question, right? Like, where is the patient admitted to, right?
Yeah.
Because, yeah, and then also the context, right? Because, and that's what's happened with the mimic ICU data. They've gone back and put where's the ER visit, right? So that it gives you a bigger context of where you are. So admissions are not all equal, right? So you have to work within a team that you can ask the subject domain expert what this means. And even for us, I'm an interventional radiologist. Harry is an MSK trained and also an ER radiologist. And when we do breast, we have breast radiologists come and tell us exactly what to do with the data. People don't appreciate how important that is, and you're going to make a mistake if you don't do it.
And I'll just add one more nuance because we're probably running short on time. Not all ICU admissions are the same, right? So you could have a patient admitted to the ICU who was already an inpatient in the hospital. You could have a patient admitted to the ICU who came straight from the ER, went straight to the ICU. You could have a patient who's an outpatient that got, or let's say from another facility that got transferred from a less well-equipped ICU to a better equipped ICU, right? So even when you look at ICU admissions, where that patient came from and their trajectory is also important. So, I mean, the decision point in a lot of these models becomes, okay, well, where do I draw the line? Because if you go far enough deep down each patient, it becomes an N of one, right? Every single patient journey is totally unique. So like, where do you draw that line of saying, okay, I'm going to group ED to ICU in, admissions together, inpatient ICU admissions together. So these are the important questions to be asking.
So hopefully most people have admissions next year's week, so we'll give it back to Saptarshi.
Okay, so these are the steps we have completed. So we did some duplicate removal, we did some imputation, filling missing values, and the last talk was about that. And then we did data merging, merge multiple tables with relevant columns that we needed for calculating length of stay. Now, again, like I said, this is only something we're doing for like a toy idea, but in practice, you probably want to include a physician team who knows the context and then decides the features that you need. After this, what you should be doing is thinking about exploratory data analysis. So then thinking of what the relationships are between these variables, thinking of what should you do with those variables, and if you have to convert some of them into another type, if you have to change some types, all of that is called pre-processing. And after the data cleaning and labeling, we get to exploratory data analysis, because without looking at what the data is, you can't do the changes that we're talking about. So one of the things we do is called label encoding, which is if green is green here, we convert it to a number 1. Red becomes 2, black becomes 3, green becomes 1. And the reason why we're doing this is because it's simpler to deal with numbers rather than the labels for it, similar to how codes are better than titles, something similar to that. The other approach is to do one hot encoding. The way that is done is basically the colors are then converted to columns, and those columns are then made into booleans or binaries. They are either 0 or 1. So if the first row, which is ID 1, is red, then only the color underscore red, that is 1, all the other ones are 0, 0, right? So two different approaches to code categorical data that you should know of between label encoding. And then there's the next process that you think of, which is called feature engineering, which is you change the way in which the representation is of a variable so that something is not given additional weight or is made more important just because the number is large, right? All of these are numbers, right? We converted them to 0 or 1 or 1, 2, 3, 4. Just because 4 is representing, or 3 is representing black, doesn't mean black is more important to us than green, right? So to be able to reduce that, what you have to do is called feature engineering, which is you have to change the way in which the data is distributed. There are multiple ways to do this. What we are trying is called scaling. So we are changing the y-axis in a way. So if you think of these two, x1 and x2 are two categories. One, before scaling, it looks something like that, the distribution of it. After we did some robust scaling, we made it similar, which means they're distributed equally, but if you see, the y-axis has changed, right? And the reason the y-axis has changed is because we've done this scaling. You can also do standardization, which is converting it into a bell curve or a normal distribution. Sometimes refer to that, or if you do min and max, which is you convert something to be the maximum value, something to be the minimum value, so you can do something like that. So all of these are different ways in which you can scale the data, and the purpose of scaling, like I said, is to not give some value more weight than it should be, right? So with that, I'll give it to Atika to talk about the second notebook that you need to work with. Atika, do you want to please talk about that?
I hope like everyone has run through all the fast notebook, the merging notebook. Once you are done with that, so once you are done with that, the first notebook, then you should have a CSV file, df underscore admissions. Everyone has this file in their directory, in their home directory, right? Yeah, so once you have that, now we will use this big merge data frame for our further analysis, especially for the further pre-processing and model development. So you should open the second notebook, which is named as pre-processing on merge data frame and training regressor. So yeah, here you may need to install two more libraries, scikit-learn and Seaborn. So please do that, run through this. Yeah, any problem until now? Okay, so once you have that, we need to import pandas and numpy, and then just read through the CSV file we just made from the first notebook. This is the notebook that we have, DF admissions. You can see there's an extra column here that we don't need. We usually get when we are reading a CSV file. So we are removing that extra column, run through that, and then as Professor said, that we may need to remove the duplicates in the merge data frame as well, but fortunately we don't have any duplicates in this data frame, but still if you want to, you can run through this.
So with the duplicates, one thing you have to do is you have to sometimes specify a column, right? So if you want unique hospital admission, you have to specify whatever is your unique hospital ID and the patient MRN, right? Because a patient can have multiple admissions. So just try to be mindful of trying to figure out what's the best pair of things that are necessary for duplicates or unique instances.
Yeah, so once we are done with like dropping the duplicates, we want to drop the rows where we have all null values, because those are basically definitely not will be useful. So we are dropping those rows, but I see that we didn't have any such rows where we had all null values. So now we want to take the data types, because previously Professor explained that we may need to do some some encoding on the data we have. So in order to do the encoding, you need to learn the data, you need to know what type of data do you have. So this df.d types shows you the data types that we have. We hear the numerical variables like admission type, or basically all the IDs like 1, 2, 3, 4, those are added here as integer or floating number, but we don't need that, these ID columns. So later on we will remove that. And also we have object files like race and long title, ICD code, those are the categorical variables. So This is what's showing from df.dtypes. So I actually checked through the columns, and I see that some columns in our data set, for example, marital status or language, we don't have any value for them. So you can like manually check from here, like if there is like any value for insurance or marital status. So I actually checked through that, so you can do it yourself. So as I saw that there is no data in these columns, basically we don't need those columns anymore. They don't give us any useful information, so we just remove that using df.drop. Once we are done, we also don't need ID columns. Those are unique for every admission. So we have removed that as well, and again, checking the data types. You can see there's some column like admit time, discharge time, death time. So these are given as in like date format, like 2019 of 26th June of 2019. So this is a bit problematic. Your model may not understand this format of the date time. So we need to change it in some other format. So what I did here is that I changed them to Unix time format. You can do it some other ways, right, Professor? Can we do some other ways except Unix? Yeah, so here we tried to do Unix format. So what it did was like the date we have here, for example, 28th June of 2010, we calculated the number of seconds that has passed from 1970, January 1st, 1970, and we put that value, the number of seconds that has passed from the initial date, and we added that here. Like you see, previously there was admit time and discharge time in date format. Now it is a long, big number that's actually representing the number of seconds that has passed. So this is how we have changed the date columns. And again, checking the data types. Here's also we are doing one more thing, like df drop na subset LOS. So what is LOS here? LOS is the length of stay. Dr. Gicho was talking about that length of stay is an important variable here. Basically, we will be building a model to predict the length of stay for each patient in the care units. So what I'm doing here is that any row that has this length of stay as null values, we are removing those rows, because if there is no values, if there is no ground truth, we will not be able to predict that. So we have removed those rows that doesn't have any length of stay. Professor, do you want to go next, like defining the categorical variables? Yeah.
So with that pre-processing done, we will now try to identify what I was talking about, which is if it's a categorical variable we want to use, make the choice between whether to use label encoder or one hot encoder, right? And both are okay, but I think there's some methods that prefer one over the other. So the modeling approach or the method, the statistical method that you're using, that would determine sort of if you want to use label encoder, which is like Boolean values, or a ranked set of values, 1, 2, 3, 4, 5, whatever, and still the model knows that 4 is not greater than 1 in terms of where it should weight it, right? So it depends on the modeling approach that you're choosing. So here you have the categorical numbers here. Sorry. Okay, so after the time changed, we're defining what the categorical variables are and which ones are continuous variables. So here you can see these ones, admission location, discharge location, insurance race, these are all categorical. That's why we're putting them under the idea of categorical variables. Death time is the only one that's not that. So we've identified those columns because we're going to deal with them, one which will scale, like the continuous variables, we are going to do scaling on them. And then the categorical variables, we're going to do a label encoder on them. Because the modeling method that we're going to choose is called gradient boosting. We'll get to what that is in a bit. But that's the, I'd say there are two main approaches today that you should choose for modeling. There are many other methods that you learn in the stats class. But if you're doing machine learning, the first ones I would say you should try is called a decision tree approach. And within those decision tree, there are two main categories that we're going to talk about. You should choose those to simplify your life because there are many of these, like there are hundreds if not nearing 1,000 types of methods to do machine learning in statistical approaches, right? And then there's a whole category of deep learning that we're not even getting into. So here we have the sample. So what we're doing is, because we should use, when we're using this computational approach that we talked about, right? Analytical approach and computational approach. The more data you give, the better it is to be able to do the computational approach. But here what we are doing, because we have limited resources and all of us are working on the same data set and server, we're going to sample a smaller piece. And here we are sampling 5% of the data, I think. So we are sampling 5% of the data and working on this. You should ideally sample or not even sample, use the entire data set if you want to build a robust model that's generalizable. So it results in 10,000 patients, as you see. And that's what we're using. Here you can sample in many different ways, right? If you go to a stats class, you'll learn that you could do random sampling, you could do stratified sampling, so on and so forth. We're not getting into that detail. We're just doing random sampling. We are selecting not the first 10,000, but randomly picking any 10,000 rows here. Okay, then the next task that we are doing is, if you saw the presentation, what we are doing here is to find correlation, right? So one thing that we did was to be able to remove the variables that, or change the scale of the variables we learned by doing label encoding or one-hot encoding and scaling, right? But the other thing you should also think of is, if the same variable is getting repeated in different ways, right? So for example, body mass index, or BMI, is containing in it height and weight already, right? So if you use BMI, you shouldn't be using height and weight as other features, because they talk about the same thing internally, right? So by doing correlation, you can identify these things which are strongly talking about the same thing, and then you should remove things that one of those, and only keep one of those features or variables in the model, because you don't want to emphasize or overemphasize one kind of feature, right? So then also you can do correlation in many different ways. Here is a snapshot of all of that you can do. So if it's a continuous variable, you can choose between these. If it's an ordinal variable, you can do that. If it's categorical variable, you can do all of that, right? When I say ordinal, what I mean is there is an order to it, right? So 1, 2, 3, 4, or stage 1, stage 2, stage 3 for a disease, right? There's an order to it. Even though it's categorical, there is an order, right? Stage 1 is less severe than stage 2, then less stage 3, right? Something like that. And categorical is where there is no order, right? Like blue, green, red color that you prefer, right? All of those colors are equally weighted. And then there are specific methods like Pearson's. If there's linear relationship, if there's non-linear relationship, if there's ranked relationship, you should choose different kinds of methods. Right? Again, like Judy suggested, you should be looking at an LLM or asking an LLM, if my variables look like these, what should I be using, right? And then what is strong, what is weak, something like that you should know. So if it's close to the line in a linear correlation, it's strongly correlated. The slope of the line will also tell you something, things like these, right? So please note the output that you get out of correlation should be interpreted in that way. So where are we on the machine learning? Now we are talking about splitting the data, right? So we've done problem formulation, we've done data acquisition, we've done cleaning, labeling, we've done some EDA, we've done some pre-processing. Sorry. Did anyone have a question? Yes. Yeah, you could do it many different ways. Like I said, you could do it using something called core plot. Will actually give you a number, or it will show you the visualization like you saw, like where the data is distributed compared to the linear line. But because it will tell you how the data is distributed compared to the linear relation that you're using. So for example, Pearson's method that you use, so Pearson is where there's a linear relationship between the variables. So you want to use that line and see how far things are from that line. And for ranked correlation, which is in one variable, what is 1, on the other one it's 1, then there's a ranked correlation. So you want to use there, and in rank correlation, a line like that won't make any sense. Whereas a heat map would, because it would still have a number which would then be comparable. So yeah, choices like that. Thanks. That is a great question. So here we are on number 5 now, the thing with split data set, right? That's the next step in the end-to-end pipeline. So like I said, 80%, 85% of the time is actually spent up to number 4. And then we get to the next part, which is sort of not straightforward, but still is more straightforward than what we just did. And then the way you split is in 2 main approaches. The first approach is called the holdout method, where you separate the testing and then build a model on the training set alone, and you don't really know in advance how your model is doing. Or the other approach is to randomly sample some part as validation, which is while you're building the model, you're going to test on unseen data. But again, finally, when you're actually going to test, you're going to do it on the test set, right? And you could do this fixed, like you do some 80% of something, 10% of the data for something, and then another 10 as test. Or you could also choose what is known as a jackknifing approach, or leave one out method, where each of those rows become your test set for the remaining values as training set. For large data sets, this is impractical to do, but a lot of times you might have to do this because you want to validate that every row is predictable or not by a model, right? So better generalization can be done with more computing, right? So there's a balance of choice that you have to make between these 3 approaches that I talked about. The other thing you should always think about is your sample weighed equally in your training and test data set, right? So a lot of times, for example, you have, I think for COVID, it's a great example. Like majority of the chest x-rays that you're going to have may not be COVID infected, right? Only say 5% of the population, at least depending on when in the epidemic you actually caught it, but only 5% are positive cases, 95% are normal cases. So you have to think of that, whether you select only 5% randomly sampled from the normal population to match the 5% of the COVID cases, or you create synthetic data for the COVID cases and so on and so forth, right? So you can do undersampling, oversampling to match the balancing of classes. So this is called class imbalance, and we're trying to match it depending, again, this is the choice that you have to make with a clinician for how the model should generalize or not generalize to what population, so on and so forth, right? So you could do stratified sampling to do it, just like I suggested with for COVID, but you could also do oversampling, undersampling. There are methods that are machine learning based called SMOT that allow you to automatically do it, but again, there are a lot of nuances in that. So talk to a clinician or administrator who will want to answer a specific question, and that's how you should undersample, oversample, or not sample it, or only do sampling and not do any of the imputation, right? Okay, so then I get to this point where we are talking about after we have done the split, we are going to choose how we are going to train the model, right? And like I said, you should only think of 2 approaches today in the current scenario, not just today, meaning today, but in the current scenario of statistical machine learning models, you truly try only 2 methods. One is called random forest, the one is called XGBoost, right? And I know there's very differing opinion among statisticians and computer scientists about this, but I'll truly tell you, from thousands of models that I've built and people have built, these are the only 2 ones that you should try today, right? Other than neural networks and so on and so forth. And the reason I say this, and I'll show you some examples of why, is because of something like this, right? And the choice truly comes down to how distributed your data is and what computation you have. When I say distributed, which means there's a diverse class presence in your data, or there's a huge imbalance within your data, and the variables that you're using to make that prediction, how much variance is in that data, right? So if you see the 4 approaches that are shown here, methods that I've shown here, light GBM, gradient and boosting, XGBoost is another gradient boosting method. All of these are ensemble methods, which means they combine many kinds of decision trees together and make a prediction. Again, you don't probably have to get into details, but the way they are done is in the bagging ensemble method. You basically look at a small subset and check what your model looks like. Then you take another subset and check what your model looks like. Then you take another subset, you check what your model performance looks like. And once you've done that, you select a combination of these outputs and you get a majority voting approach and build a model. Like that's what you do in the random forest broadly. And then there is the boosting method where you build all of these models, but use the output of one model to feed as the input to the other one. Basically the errors, right? Not the correct predictions, but the ones that were incorrectly predicted. You use that to the next model, becomes the input. These are called residuals in technical terms. But these residuals then go to the next one. They become highly weighted, so I don't want to make a mistake on these specific ones that I made a mistake on earlier in this new tree that I'm creating. So I change the weight, which is why if you think of it, this will be more intensive, right? Because it takes more time, and like you saw here, it is supposed to take more time, but then there are interesting libraries that can do this parallelly, and that's why XGBoost does better than gradient boosting, which is what I'm trying to show you, is much slower than the bagging method, which is random forest. But today, because of parallel processing, boosting methods are feasible to do in this, right? So like I was telling you, so you take the first model, weight it differently, the errors that you've made, and then again train the model. Again, where you've made an error, you take it there to the next one, you take to the other one. So finally what you get is a model that ideally performs better than each of the individual trees or the first attempt that you made in the tree prediction. So any questions on this? I know I've gone too fast on this topic, but again, like I said, these are the only two methods you should really focus on to in the current world. The gradient boosting method and the bagging method, random forest. Yes?
Not like TDM, it has better accuracy.
Yeah. It's another approach to do gradient boosting.
So is it better to use XGBoost and random forest? Yeah?
Those are the two methods you should choose between.
Okay, so why not like TDM?
You could. It's just a different library that implements parallel processing slightly differently. But it does not make all possible attempts. So there's a chance that you're overfitting to a specific thing rather than generalizing better. So XGBoost generalizes slightly better than LightGBM, but again, depends on the use case. But like I said, there are two main things you should focus on. Both are ensemble methods that combine trees. One is using bagging and other pruning, and the one is using boosting. Yes? From training. Yeah. Any other things? Any other questions on this? Okay, the reason why, now I mentioned that there are these two approaches only that you should think of. And the reason for those are the explainability of these models that allow for trust of clinicians in making a decision from the model or choosing that the model's decision is valid or not. Because you can do things like these, which is to tell you if this variable was more important than the other in making that decision that the model made, right? So the explainability of a tree model is much more easy to understand. People have done human studies to explain or to understand if an explainable model is more explainable through a tree model or through a regression, like a linear regression model, or through a boundary model, which is called SVM. We've seen that tree models are much more explainable, are much more understandable by individuals in their response, which is why I mentioned those two approaches, which are decision tree models that you should be using. And then there is univariate and multivariate. There's fit time, predict time, target required, target not required, that allow you to choose which method to look at. Okay, so everybody please run the notebook on the next part, now that you've understood the concept behind this. Please, I know we are waiting for lunch, another maybe 10 minutes, and we'll try this out. So please plot the correlation here. You can see the table of correlation, and you can also see the yeah, so you get a correlation plot that looks like this, showing the different correlation. We are splitting the data. Like I said, the scaling that we have to do for continuous variables, that's what we are doing here. And we are choosing a histogram gradient boosting approach. Like I said, you can use the other ones. They're a little more intensive, time consuming, so which we are avoiding here. But again, you could use XGBoost or Light GBM for doing gradient boosting here. Once you've built the model, like after you've split it, this is as simple as how you build a model, model.fit. So it's that just one line that allows you to build the model. And then after you've built the model, you want to see which ones are more important. So as you see, the last care unit, the first care unit are important for predicting length of stay. Discharge location is next important. Admit time, insurance, surprisingly, plays a role. Surprising or maybe not surprising for people who worked in the ER. Race, ICD code, title, again, shouldn't be used. If you died at the facility, of course, your length of stay is cut off before you recover. So these are more important variables that you can see. Again, now you can actually plot a tree out of this and look at what the tree looks like. So internally, which feature was what value, you can look at all of them and get a tree out of it in this.
Just a comment about the feature importance there. This is where you again have to go back to your domain expert, right? Because this is not telling you anything about the patient, right? You have to understand why is the patient admitted in this unit in the first place, right? This just gives you a question to ask because this is like